Welcome to the Explainer. Today, we're diving into a really cool concept that bridges the gap between abstract algebra and visual geometry. We're talking about the graphical solution of simultaneous linear equations. Essentially, we'll see how we can use visual graphs to actually solve math equations, turning a bunch of numbers and letters into clear, actionable visual lines. It's going to be a lot of fun.
But before we get totally lost in the algebra, consider this for a second. How can drawing two simple lines on a grid predict a business's exact profit? I mean, it sounds kind of like magic, right? But it's pure math. By the end of this explainer, I promise, you're going to understand exactly how to use these foundational mathematical principles to solve a very real, high-stakes business problem.
So, here's our roadmap for today. First, we'll look at graphing single linear equations. Second, finding the unknowns. Third, solving simultaneous equations graphically. Fourth, we'll dive into those real-world business applications. And finally, we'll cover the three-line possibilities.
Let's kick things off with Section 1, graphing single linear equations, because, every complex graph really just starts with one simple line.
Now, before we draw anything, we've got to know what we're actually drawing. Our fundamental building block here is the standard linear equation. You've probably seen it, ax plus by plus c equals 0. Here, x and y are our variables, and a, b, and c, well, those just represent the defining constants that lock in our line's position.
So, how do we turn that algebraic equation into a visual line? We just follow 5 foolproof steps. Step 1, make x or y the subject of the equation. Step 2, pick at least 3 suitable values for the variable on the right-hand side. Step 3, construct a table to organize those different pairs of values so things don't get messy. Step 4, plot those ordered pairs as dots right onto your graph paper. And finally, step 5, just draw a straight line passing right through those points. Easy enough, right?
Okay, let's actually see this in action. Take the equation, 3x plus y minus 4 equals 0. First up, we make y the subject, which turns the equation into y equals negative 3x plus 4. Next, we pick 3 simple, easy-to-work-with values for x. Let's go with 1, negative 1, and 0. Plugging those right into our new equation gives us the corresponding y values, 1, 7, and 4. We drop all of those into our neat little table. Then, plotting those coordinates, 1, 1, negative 1, 7, and 0, 4, gives us our perfect straight line.
Moving right along to Section 2, finding the unknowns. Once that line is drawn, it actually becomes a super powerful tool. Take a look at the graph for the equation 2x minus 3y plus 12 equals 0. Suppose we know for a fact that a point lies on this line, but we only have half of its coordinates, say the point m, negative 2. Well, because the point exists on the line, we can just go to negative 2 on our vertical y-axis, draw a horizontal line across until we physically hit our graphed equation, and then drop a vertical line straight down to the x-axis, and boom, it lands perfectly on negative 9. So our unknown m is literally negative 9. We can do the exact same thing to find the unknown n for the coordinate 3, n. Just start at 3 on the x-axis, go up to the line, trace across to the y-axis, and we find that n equals 6. Honestly, the graph does all the heavy lifting for us here.
All right, Section 3, solving simultaneous equations graphically. This is where the real magic happens.
So here, we've plotted 2 distinct equations on the exact same graph. We have 3x minus 2y equals 4 and 5x minus 2y equals 0. Notice what happens when we do this. These 2 completely separate straight lines cross at exactly one location, point P, down at the coordinates negative 2, negative 5. Now, the absolute crucial takeaway here is that this intersection is not just some random dot on the paper. It is the definitive, unique solution that satisfies both equations at the exact same time. That visual crosshair literally gives you the exact algebraic answer.
Which brings us perfectly to Section 4, real-world business applications. Let's see why this mathematical intersection actually matters in the real world.
Imagine you're consulting for a factory that manufactures, say, basic retail articles. We have some raw data right here. That top row, X, is the number of articles produced. The middle row is the cost price, or CP, basically what it costs the factory to physically make them. Notice it starts at 20 rupees. Even if 0 articles are made, that's going to be your fixed overhead costs, and it scales up to 180 rupees for 80 articles. The bottom row is the selling price, or SP. That's the revenue coming in. Obviously, selling 0 gets you 0, but selling 80 gets you 200 rupees.
Now, staring at a table of numbers like this can be a bit confusing. How do we quickly figure out when the factory actually starts making a profit?
Well, to answer that instantly, we just turn our data tables into two simultaneous linear equations and graph them. The line starting at 20 on the y-axis is our cost line. The line starting down at 0 is our sales line. Initially, you can clearly see the cost line is riding higher, meaning the factory is losing money. But look right at where they cross. Just like in our previous abstract math example, this intersection point represents something profound. In the business world, the exact moment that sales line crosses above the cost line is known as the break-even point.
If we trace that intersection straight down to our x-axis, it lands precisely on the number 40. That means the factory must manufacture and sell exactly 40 articles to reach a state of 0 profit and 0 loss. If they only sell 39, they are in the red, but if they hit 41, they are officially making money. We just solved a pretty complex business dilemma simply by finding the intersection of two straight lines on a graph. How cool is that?
Let's wrap things up with Section 5, the three-line possibilities.
So when you draw two straight lines on a flat plane, they don't just have endless, chaotic behaviors. In fact, they can only ever do one of three things. First, they can intersect at exactly one point, just like we've seen so far. Second, they can be perfectly parallel to each other, like railroad tracks, meaning they will absolutely never cross. Or third, they can be what we call coincident. That means they lay perfectly on top of one another, effectively forming a single line where every single point is shared.
And what's really amazing here is that we don't even need to draw the graphs to know which of these three outcomes we're going to get. We can actually just look at the algebraic ratios of the constants in our two equations. If the ratio of the x coefficients, that's a1 over a2, does not equal the ratio of the y coefficients, b1 over b2, the lines are absolutely going to intersect, giving us one unique solution. Now, if those first two ratios actually match, but they don't equal the ratio of the c constants, the lines will be perfectly parallel. They will never ever touch, meaning there is mathematically no solution. And finally, if all three ratios are completely identical, the lines are coincident. They're essentially just the exact same equation in disguise, meaning they touch everywhere, resulting in an infinite number of solutions.
We've seen firsthand how a unique intersecting solution gives us a factory's precise break-even point, right? We totally understand the practical, real-world value of finding that one perfect coordinate. But I think this leaves us with a pretty fascinating final thought to ponder, based on those rules of ratios. If coincident lines share all points across their entire length, what does having infinite solutions actually look like in a practical day-to-day scenario? What kind of business or scientific dilemma has literally an endless number of correct answers? Something to think about. Keep exploring, keep graphing, and thanks so much for joining me on this explainer.